Welcome to DCL 103. If you are really new to radio and electronics, you probably want to watch DCL 101 and 102 before you watch this video. In any case, this video will be about inductors and inductive reactance. Inductors and capacitors are of primary importance in the field of radio. And of course, all my videos are primarily about the world of radio. So what are inductors? Well, inductors are simply coils, that is, coils of wire, usually wound in a circular pattern like shown here. Terms we're going to be using are induction, inductance, and inductive reactance. I won't go out of my way to give you a definition of either of these three terms. I hope that you will form a definition in your head as we go through the video. At the end, I'll show you dictionary definitions, but I'm not always very happy with dictionary definitions, and you'll probably see why by the end of the video. So here are two more inductors. The object in the foreground is a resistor, a 2-watt carbon composition resistor. It is just over a 1/2 inch long. I included it so you can get an idea of the size of these devices. The device in back is a 6 Henry power supply choke. That is a tremendous amount of inductance. It is wound around a iron core like a transformer to greatly increase the amount of reactance you can get out of it. The little black object is a 100 microhenry coil. Now 1 microhenry is 1/1,000,000th of a Henry. So clearly, this little 100 microhenry coil doesn't have very much inductance. Here, I've taken the jacket off it. It is just some enameled wire wound around a core. Now, that is not a magnet. That is a piece of material that has high permeability. That means it conducts magnetic lines of force really well, kind of like the iron core in the big choke. Now, this little coil, as I said, has only 100 microhenries of inductance. I'm now going to show you a coil, and my memory eludes me. I think it's 9 microhenries. So 1/10 of the inductance of this coil is present in this coil, which is approximately 2.5 inches diameter by 6 inches long. I made this out of copper tubing, 1/8 inch copper tubing, to base load a 20-meter vertical antenna that wasn't quite long enough to be 20 meters. So I added, I think it was about 9 microhenries of inductive reactance to it, and that fixed my problem. Now, first thing we got to talk about, this is very important, and you'll see why in a few minutes. We're going to talk about voltage, current, and phase. Think of a DC circuit. Now, in the next several slides, I will be showing you a graph on top of a graph. The upper graph is the voltage. The lower graph is the current that resulted from the voltage. In this case, you'll notice as soon as I turn my power on, my current rises as well. As the voltage stays steady, the current stays steady. When I turn the voltage off, the current drops to 0. So we would say voltage and current are in phase because they happen at the same time. It can be the same in an AC circuit. As the voltage rises, the current rises. As the voltage starts to drop back to 0, the current falls back to 0. As the voltage reverses polarity, the current starts going in the opposite direction. Notice at the beginning of every cycle, things are in phase. In fact, in the middle of a cycle, things are in phase. So everything's in phase. We would say that this is a perfectly resistive circuit because resistance does not change the phase between the voltage and the current. It can't. Now, before we move on, Let's say we have a voltage. It results in a current. We lower the voltage. What happens to the current? Well, it goes down. But let's look at it a different way. Let's say we have a voltage. We keep it the same, but we raise the resistance. Well, the current goes down. What if we drop the resistance really low? Well, the current goes way up. The important thing here to notice is no matter what I do, everything stays in phase. Everything happens at the exact same time. Because remember, the horizontal axis is time going into the future. So everything stays in phase in these circuits, both DC and AC. So voltage causes a current to flow. The current is a direct result of the applied voltage. The current goes up and down with the voltage, but the current varies inverse proportion to the resistance. Current is always in phase with voltage as it is a direct result of voltage. This applies to any resistive DC or AC circuit. Let's stop and talk about induction for just a few minutes. Induction is where you use an electric or magnetic state and you produce an electric or magnetized state in another object by bringing the two close together. The transformer does this really well. Here we have a voltage causes a current. The current creates a magnetic field. The magnetic field induces a voltage which causes a current over here. So in the transformer, we use the property of a magnetic field to produce an electric current in the secondary. And it works really well. That is induction in transformers, and that's how we normally use induction, is in AC circuits. Because remember, the magnetic field has to be changing to introduce any kind of voltage or current over here. Well, in AC circuits, particularly sine wave circuits, the current and the field constantly change. So induction in an AC circuit really works well. What about induction in a DC circuit? You wouldn't think it would be important, and it kind of almost isn't, but it's good to understand it. I'm not going to go over the definition another time here. Let's just look at this instantaneous voltage in this wire causing an instantaneous current which makes this magnetic field pop into existence. The current flow creates the magnetic field. But induction is only a result of a changing magnetic field. The current changes here and here. So when do we have a changing magnetic field? Well, we only have a changing magnetic field here and here, so we only have induction here and here. So the green wire only gets a tickle when you turn the power on, and it gets a negative tickle when you turn the power off. This is because the magnetic field expands here and contracts back toward the black wire here. So induction in a DC circuit happens but it only happens when the field is changing. So it's not super helpful or important in a DC circuit. We just want to remember that it's there. What about induction in AC circuits? Well, as I said before, boy, does that work well. And I've already explained why it works so well. So induction works really well in an AC circuit. So what's inductance? Inductance is what almost what makes radio work. Let's go back to our electric current in our wire. Now, it's important to understand that the changing field produced by the current in the black wire causes what we call a counter EMF in the second wire. This is called an active induction when the field, or when the effect of the field, is felt in the green wire. So here we're back to induction. Let's make the leap to inductance. Let's have our wire wrapped like a coil. We start current flowing, so magnetic lines of field come into existence, and they're not just there at those two little curves. They're everywhere along the wire, from here all the way to the bottom. But I'm just showing you two of them. But they're everywhere here. They're all the way around the wire. As they expand out from the wire, if you pass enough current, or if the windings are close enough together, they team up together. And then when you turn the current off, they collapse together. Remember what I said earlier. The changing field causes a counter EMF in the second wire, and we call it induction. But now the counter EMF is being created in the very wire that started the current in the first place. So now the counter EMF is opposing the very current that started the whole process. The act of induction is now defined as inductance because the effect is occurring in the same place that the cause of the effect is happening. So, as the field expands, because current is increasing, inductance resists the current flow. As the field collapses, because the current is decreasing, remember that negative kick I showed you, now inductance boosts the current flow. So the inductance is trying effectively to stop any change in current. When the current rises, it tries to keep it from rising. When the current falls, it tries to keep it from falling. In this definition, you could say the inductor is storing the charge. And it doesn't charge it or store it for very long, obviously, but you could say the inductor is storing the charge. But more to the point, inductance is the tendency of an electrical conductor to oppose a change in the electric current that is flowing through it itself. So now we're going to go back and talk about phase versus inductance. So the counter EMF in the coil is causing two things to happen. The current is being reduced by the counter EMF, much like a resistance would reduce current flow, because the counter EMF is really an opposite voltage. But there's something else that's happening. The current is delayed by the counter EMF. When the current tries to rise, inductance tries to keep it from rising. When the current starts to fall, inductance tries to keep it flowing. Remember I showed you in a resistive circuit, everything was in phase. Here is a circuit with a tremendous amount of inductance, but no resistance, just a lot of inductance. Now, when you first apply voltage, the current is still going to flow. But after you've gone through several cycles, what you end up with is what I'm showing you here. So after, let's say, a few hundred cycles, once you turn the power on, the current, every time the current rises, the counter EMF tries to slow it down. So after several cycles, because you have no resistance, which by the way is impossible, but let's pretend that you can have a coil with no resistance for just a minute, okay? What will happen is the delay builds up to the point that the current is always falling 90 degrees behind the voltage. Now, what do I mean by 90 degrees? We assume we describe this full cycle as 360 degrees. But the current is a quarter of a cycle late. What's 1/4 of 360? Well, it's 90. So we say the current is 90 degrees lagging the voltage. Now again, when you first turn the power on, the current is in phase with the voltage. But after you've gone through a few cycles and this delay builds up, when you get to what they call the steady state period, meaning several cycles after it starts and now everything is in sync, you actually would have this much of a delay. Now again, you can't really have 90-degree delay because you can't have a conductor with no resistance, but you can get darn close to 90 degrees. So think about what's happening. The counter EMF is trying to reduce the current, but it's also delaying the current. And remember, as the current falls, the counter EMF puts a kickback in there. Remember that spike from the DC circuit? So the counter EMF, whatever the voltage is in the wire, the counter EMF is fighting it. And if the voltage is falling, the counter EMF tries to boost it, tries to kick it and keep it going. Let's say you had equal amounts of inductance and resistance in the circuit, which is a lot more reasonable of an estimate. Now you only have half the delay. So now when you get to 45 degrees or 1/8 of a cycle, now the current starts. And again, this is after several cycles after you turn the power on that you're going to be at this state here, where the current is actually 1/8 of a cycle late. Now, in a real circuit, because the ratio of inductance to resistance can vary so much, the phase difference can be anywhere from like 1/10 of a tenth of a tenth of a tenth of a tenth of a degree to 89.999 degrees. You'll be somewhere in between. If you take all the inductance out of the circuit, the voltage and current go right back into phase, which is what you show here. Everything's in phase because there's no inductance at all. You straighten the coil out to a straight wire and there's no inductance. So what's inductive reactance? I'm going to define this one for you. Inductive reactance is the effect on the current that is a combination of reduced current and delayed current. This total overall effect we call inductive reactance. By the way, it's measured in ohms, just like resistance is. It limits current flow, just like resistance does. But it delays the current flow, which resistance does not do. Now, the next video, I'll talk about how to calculate the total resistance when there is both resistance and inductive reactance, and I'll talk about impedance. I'll give you a little preview, and that is a circuit with resistance plus reactance is said to have impedance. But there's something really clever. Once you calculate your impedance, you can use Ohm's law and put the impedance number where Ohm's is supposed to be, and the formula actually works. But that's going to wait for the next video. I promised to give you the dictionary definitions. I'm going to throw them up here. I don't see a reason. I don't want to talk about them. If you want to freeze the video at this point and write those down, go ahead. You might find that they don't really completely describe what you just learned. And that's the problem with the definitions. I don't necessarily really like them. I pulled them out of a regular dictionary. If you pull them out of an electronic dictionary, the definitions get a little better. Okay, two more things, or two final things. In the next video, DCL 104, I'll introduce you to the formulas for inductive reactance and inductance and show you how to come up with how much inductive reactance you have in a circuit. But more to the point, I'll introduce you to the idea that you can look at a formula, not do any math, and by looking at the formula, say, hey, this formula tells me the following things about how the circuit will act. What I'm stressing here is I've seen other instructors really get excited that you understand how to use the formula, and yes, that's true. But I think what you first must understand is what's the formula telling you? Apart from math, when you look at the formula, what does the formula tell you about how the circuit acts? And I'll introduce you to that concept in the next video. Now, there's kind of I guess this is a correction. It's a correction to some shorthand I used earlier in this presentation. I may have implied that magnetic lines of force only form around the wire when the wire is in the shape of a coil. Well, that's not true. Any conductor carrying current will have magnetic lines of force around it. Now, can a straight piece of wire have inductance? The way I explained it, it probably sounds like it can't. Well, it can. A straight piece of wire will react to its own magnetic field, although the reaction is extremely slight. It is something that in radio we have to know about and we actually can take advantage of. And I'll talk more about that in DCL 104. So thanks for watching. I hope this was a well-spent 20 minutes and 30 seconds. And I'll see you in DCL 104.